Hello, everyone. So today I will be presenting my 2024 William and Mary Graduate Honors Research Symposium presentation, the alternate one. My name is Zannatul Shahla. I am working under Professor Jonathan Scheerer. The title of my project is Synthesis of Pyridine Derivatives, Cycloaddition/Cycloreversion of 1,4-oxazenone intermediates. So some background, 1,4-oxazenones are an understudied heterocyclic ring system that can undergo a merged cycloaddition/cycloreversion sequence, leading to the production of pyridine derivatives. They have synthetic utility in their own right, but why do we care that they are the most reactive intermediate to get to pyridines? Pyridines are an important heterocyclic ring system that are frequently found in bioactive molecules, and the second most common nitrogen-containing ring structure present in FDA-approved therapeutic molecules. Oxazenones are the most reactive heterocycle for cycloaddition-based strategies to get to pyridines. However, the understanding of oxazenones is limited, and the literature present right now is simply not enough reaction pathways have been studied to get to pyridines. So on the right, I have a general scheme of how the cycloaddition-cycloreversion pathway works. The oxazenone, which is in red, is reacted with an alkyne to undergo a cycloaddition product, which is the bridge intermediate. Then CO2 is extruded in the cycloreversion pathway, and then we get the two pyridines observed on the right. Existing methods for 1,4-oxazenone synthesis include using cyanohydrin and oxalochloride at elevated temperatures to afford a 3,5-dichloro substituted oxazenone. The issue with this pathway is that it is toxic, cyanohydrin is toxic, and the reaction conditions of 90 to 132 degrees to get the desired oxazenone is unfavorable. And we only have one substitution area, one place where a different R group can be added. Another method for 1,4-oxazenone synthesis has been done by the Scheerer lab, where azodiacrylate derivatives, so the molecule on the left side, undergo a Staudinger reduction using triphenylphosphine to give us the oxazenone. This then it tautomerizes, as shown with the equilibrium arrows, to afford the oxazenone that can undergo a cycloaddition/cycloreversion with an alkyne to afford a pyridine. This method, again, while works, again, only offers one R group. The new method that we are looking at uses beta-amino alcohol precursors, which are readily available commercially, and reacting them with dimethyl-acetylene dicarboxylate, or DMAD, to give us to afford a isoconjugate addition, which then lactonizes to give us the lactone ring that is after the DMAD arrow, which then is brominated and dehydrobrominated using base to give us the oxazenone, which then again, with showing with the equilibrium arrows, gives us the tautomer that can be reacted in cycloaddition/cycloreversion to give us the pyridine. This pathway both utilizes commercially available starting material, and on top of that, gives us different various substitution patterns with R1 and R2. So again, the preparation of pyridines, we used the oxazenone that we just talked about using the new scheme, and a model alkyne phenylacetylene to do a cycloaddition/cycloreversion to afford us the two stereoisomers, a 2,4 stereoisomer and a 2,3 stereoisomer, basically based on where the phenylacetylene is adding. The results here show a table of 7 beta-amino alcohols that we have successfully turned into 1,4-oxazenones using this pathway described, and then on top of that, the cycloaddition/cycloreversion to get to the pyridines. Again, regioselectivity of where that phenylacetylene is going to add is not defined, as different substrates have different regioselectivity. Some future research is applying this pathway to natural product synthesis. So currently in the lab, we are working on xylanogrypin-A to get, by using this scheme and reacting it to afford this natural product, which has tranquilizing effects on the central nervous system. Future research will involve using different beta-amino alcohols to expand this library and to show proof of principle that this scheme does in fact work. And here are my references, and thank you.